Morning, everyone. Welcome back. So you may have seen in Slack, I did last night address, or I hope I addressed it, I didn't actually test it, but I think I found the issue with the debouncing logic, and hopefully if you pick up the change, that'll be fixed. So next time we do builds, we can make sure we've got that fixed. So just to do a quick review, bear with me as I just look back over the old slides. So we've been stepping through the basic concepts of digital logic, right? Logic gates, composing logic gates into combinational logic, adding in the concept of time with sequential logic, how we code that in transaction level Verilog, implying the flip-flops. So using the greater than 1, for example, as referencing the previous value to imply a flip-flop. We looked at pipeline logic. Ahead. Where you're putting your logic in the context of a pipeline and using that context to imply the flip-flops that carry information through the pipeline. We looked at various online design tools, right? First NAND game, and then Walkwe, both being sort of drag and drop schematic style logic design tools. And then we transitioned into microchip and used transaction level Verilog to express our logic. We worked on the calculator circuit. We hooked up the inputs and outputs of our calculator to do the 7-segment display and take in inputs from the user. We created the edge detector to be able to only operate when the button was pressed, or in our case, the switch. And so I think we left off here. We looked a little bit at the both the FPGA build flow and the ASIC build flow, and looked at the the 3D viewer for our ASIC silicon. So today we're going to shift gears into software and relate the software stack with how that software gets executed on hardware. How many of you are familiar and comfortable with the RISC-V instruction set? I think it was fairly few of you. Okay. How many consider yourselves competent programmers in any language? Doesn't matter. Good. So starting from a high-level program, right, your program gets compiled into a binary file. The binary file gets loaded into memory on a CPU, and the CPU is responsible for executing those binary instructions out of memory. The binary file is not very human readable, so we have a human readable representation of the machine instructions known as assembly language, assembly code. So the compiler is able to go, maybe straight to binary or straight to assembly code, and an assembler will take you from assembly code to binary. A disassembler will take you the opposite way. The instruction set architecture is a definition of the binary encoding as well as the human readable assembly code representation of that encoding. This is kind of the contract between the compiler and the hardware. Right? The compiler produces this format, the hardware executes it. So for example, x86, ARM, MIPS, RISC-V, and so on. There are some slight variations on this theme. Java, for example, compiles into a bytecode. It's not expected that the bytecode, so in this picture, this would be the byte code. It's not expected that the hardware is natively executing the byte code. We expect there's a runtime compiler in the flow that's translating from the language-defined byte code defined by Java into the hardware's instruction set architecture or byte code, and then that byte code executes. Okay, so this binary file is portable across platforms. Every platform has their own runtime compiler that can execute it. So you pay a little bit of cost in runtime compilation, especially upfront when you execute your code, but re-executing the code, it's already been compiled. They'll also build in some runtime optimizations to sort of recompile based on the dynamic nature of the program. WebAssembly is another one, an exciting one, kind of addressing the last shortfall in web technology performance. So you can run bytecode from the browser instead of JavaScript. So what we're going to be doing is looking at this entire stack using tools online. So we're going to use Compiler Explorer and MakerChip running the Warp5 CPU generator. So Compiler Explorer is going to let us surprisingly explore compilers, right? Play around with high-level programs, compile them, understand how they get turned into assembly code, and correlate the assembly code with the high-level program. We can take that assembly code and drop it straight into a RISC-V core that we build and run on MakerChip. That code, the Warp5 CPU generator using TL-Verilog has a built-in assembler. It uses the macro preprocessor that we layer on top of TL-Verilog. So you can drop your assembly code straight into there. When you compile your, your code, the macro preprocessing assembles your code, turns it into bits, creates an instruction memory that's hard-coded with those bits, and you execute your code out of there. So we'll do that and use the visualization in MakerChip to understand how the hardware is executing our assembly code. Right, so this is going to give us a view of the whole stack. We can play around with assembler options. We can use different programming languages and see how that's turned into assembly code, see how it's turned into binary, execute that code on a CPU that we configure and build to our choosing, and and see everything from high-level software to execution. All right, so first I'll demo. So Compiler Explorer is at godbolt.org, and I remembered incorrectly the first day. This is the one with the crazy long contract that says we're not going to do anything bad. So you can go ahead and accept that. So by default, it comes up with this simple program that's just a function to square a number. And you can see the assembly code. 5. So the first thing I'm going to do is configure this for RISC-V. Right, it's defaulting to x86. This pull down has a bazillion different assembly languages. Sorry, not assembly language. Different instruction set architectures that you can utilize. So I'm going to use this pop-up, which is a little bit easier to navigate since there are so many. And this will let me click on, who sees RISC-V? It moved on me. Here it is. RISC-V 32-bit. And I want GCC trunk, this one. So this is RISC-V assembly language, compiling this square function. You can also play around with the compiler options, and maybe I'll make this a little bigger. So I'm just going to cheat and cut and paste here. So to be honest, I don't know what all these options are, but I think this is march is, I think, the machine architecture. It's specifying that we want RISC-V 32-bit, and I is kind of the base support for RISC-V. RISC-V defines a bunch of architectural extensions that add support for other things, like M extension is integer multiply and divide as an instruction. So this is just the bare bones instruction set. Sorry? Yeah, good idea. So I'm not exactly sure about the ABI. And then O2 is an optimization level. So we can change the optimization, for example, to O0. That will immediately compile. You see the code is longer, right? It's unoptimized. So you can experiment with different optimizations. 3. So I'm going to stick with O2. And over here you have, again, a very, very long list of different programming languages that they have support for. And I'm going to stick with C++, but you're free to play around with the other ones. There's a whole bunch of other options here. I'm not all that familiar with all the intricacies of the platform. Okay, so demonstrate the whole flow. So I've got my squaring function. I'm going to copy that and then go to microchip. Actually, sorry, I'm going to go to warp5.org. I've done so many talks in the past week that I was losing track. I did not show this before, right? warp5.org. Okay. So warp5.org is a configurator for this TL-Verilog CPU generator. Okay. So here we can configure the CPU that we want to build. I'm going to build a RISC-V CPU. I think I'm just using the defaults here. Okay. So we've talked about pipelining, right? Right now it's configured by default as a CPU that's implemented in a 4-stage pipeline. If we want a simpler, lower performance CPU, we can choose a single-stage pipeline. Or a more performant core, we can stretch it out over 6 stages. I'm going to stick with the 4 stages. Architectural extensions for RISC-V, I'm going to leave it as it is, so it's just the I base type, base extension. And I'm also going to enable a custom program. And I'll just paste mine here. So the one that I copied from Compiler Explorer, I'm going to paste here. And set to latest. I'll try that one. You can select the version of warp5. I'm going to use the latest. So I think that's what I want. Scrolling down here, I can see the configuration that I've just built. Here's my test program. So this is the code that I'm going to load into microchip. You can also see here, this is the source code. After the macro pre-processing, we have kind of clean TL-Verilog code. We can see that here as well. And that becomes our TL, which we can also see. But we can also explore this in MakerChip. So back to the configuration, edit in MakerChip. And that should bring up a RISC-V core executing our test program that we created in Compiler Explorer. So the code that we compiled in Compiler Explorer is not a complete application, it's just that one function, the squaring function. Right. Okay, we don't need the diagram, we'll just look at the viz. So we've compiled our core. What we're looking at here is all of the state of our CPU. So we've got the instruction memory that contains the test program that we just dropped in place. This logic is interpreting those instructions as it executes them. So the instructions will fetch out of the instruction memory, get interpreted. Instructions. So again, trying to remember what we talked about. Okay, so RISC-V is what's called a load store architecture, which means the majority of the instructions are operating on values from the register file. Okay, so we have a register file with 32, actually 31 values that instructions can read and write. And we have memory. The instruction set architecture has specific instructions to access values to and from memory, so loads and stores. We also have a more detailed view here of our up here for now. So we can step the simulation. There are going to be several cycles of reset where we're not doing anything. And here we execute the first instruction of our test program. So this pointy hand represents the program counter. The program counter is telling us what instruction we need to execute next. That instruction gets fetched, so read from the instruction memory. Then the decode logic figures out what the instruction is. Right? Just 1 second to look back. Okay. So the decode logic figures out what the instruction is that we want to execute. So in this case, it's figured out that the instruction is an instruction called add I, which stands for add immediate, which means it's performing an addition, and one of the values that it's adding is an immediate value, meaning that value came from the instruction bits themselves. So if you look at this instruction, it has this -16 value. That -16 value is encoded in the bits of the instruction, and it's referred to as an immediate. The other source value is coming from the register file, from this register that's referred to as SP, which stands for stack pointer. So we're adding the stack pointer register to -16 and resulting in a -16, which we write back to the stack pointer. So this instruction here, this first SP is the destination register, the register we write to. This is the register we read from, and this is the immediate value. So that's the nature of RISC-V instructions, and similar for most instruction set architectures. Very typically up to two source registers, potentially an immediate value from the instruction, and a destination register. And the machine is just going to keep fetching instructions one at a time, performing the operation, and writing back the result into the register file. Right, so I can just play the execution. We can see the code execute, right, one instruction at a time. So this was not a very exciting test program. We just executed a couple instructions. We could play around with something more interesting, perhaps. Let's go back to Compiler Explorer, and let's see what's more interesting to do. Let's do a factorial. So we'll take in a value, and to compute factorial, right, we need to multiply, if we're doing 10 factorial, it's 10 times 9 times 8, etc. So maybe we can, I'll do the variable return. That's what we're going to return. So maybe I can do int return equals the number to start us off. And while the number, and correct me if I mess something up here, is greater than 1, I haven't coded C++ in a while, so be kind. We will multiply the return value. I guess we can do times equals. Do num, and then subtract num. And if we do a main, so I want main at the top, so it executes first. I think that might cause an issue. I think we need to declare factorial. Something like that. I might have this wrong. Looks like it actually compiled, so that's a good thing. Anybody notice any mistakes? All right, I'm going to trust you guys. So let's take this program and drop it here. And I want to have this indented. Okay, everybody cross your fingers. The assembler that's built into MakerChip is not necessarily the most robust assembler. To be honest, there's very little documentation on assembly code syntax, so a lot of it was experimentation. But it looks like it compiled. Let's see if it actually initializes properly. So the CPU that's built, and the simulation that's run, is just going to start execution at the top of the program. So all right, so first instruction, jump. So this is a jump, which return. Oh, jumping link, okay. So I believe this is branching to or jumping to the factorial function, but let's see. Just going to let this play. So there are, actually, I think what I'm going to do is simplify this a little bit. No, that's going to be too hard to do. Okay, so I've built a core that is a 4-cycle pipeline. Most cycles, it's going to execute an instruction. Some cycles, it's going to make mistakes. Those instructions will not commit. And in the simulation, we'll see them in gray. So it's only the light blue instructions that we're seeing that are actually part of the execution of the program. We'll talk more about those, all of that detail as we go through the course and implement the RISC-V core. But for now, just understand that it's only the cycles where this is cyan color that are meaningful. I'm going to slow this down. Oops, I sped it up. Slow it down. So I'm not sure why we went back to the top of the program. Maybe there's an issue here. Well, that doesn't look right to me, so let's see if we can figure out what happened. Or why don't I put that aside and we'll get back to that later. How many packets do we have over there for the cards? Okay, so we're going to hand out packets for packets that represent the state of RISC-V CPUs, and you guys are going to have an opportunity to be RISC-V cores. So I'm going to put this aside and come back to that later. So while those are being handed out, this slide shows some example RISC-V instructions. So we talked about this just now in Work 5, looking at Work 5, looking at the visualization. But again, on the left, you've got instruction mnemonics, right? So these instructions represent, each of these instructions is 32 bits in the instruction memory. And those 32 bits are encoding the information here. So the type of the instruction, in this case an add instruction, the destination register, sometimes, and 2 source registers. Okay, so this instruction operates on 2 source register values and produces a value to write to a destination register. An instruction that has that format is referred to as an R-type instruction, register type. We looked earlier at add I. So this is an add I that has an immediate value, in this case 10. So destination register, source register, immediate value. You have other instruction types. We have branch instructions. This BLT, for example, is a branch if less than. This is going to, so typically you execute an instruction, you increment the program counter, and execute the next instruction. Increment the program counter, execute the next instruction. A branch is going to take you to a different instruction. So the branch instruction is given a label. The label identifies an instruction in the program, and the branch instruction, if the branch condition is true, will take you to that instruction next instead of falling through to the next instruction. So the LP label, when you assemble the code, is turned into an immediate value that represents an offset from the current instruction that will take you to that instruction. So the assembler figures out the label is to a particular instruction address, computes the offset from the current address, and then encodes that in the instruction. Okay, so just talking through kind of the nature of assembly code. And we're going to kind of step through the definition of the RISC-V instruction set architecture and understand all this in a level more detail. So at this point, and I don't think we have the program counters for you, so you'll have to make up something for the program counter. But what we need at this point is just this instruction memory card. This is meant to be a double-sided card, but we've printed them single-sided. So there's a corresponding instruction memory card that has mnemonics on it. I think that one's on paper. So, so you should have that instruction memory front and back, and the register file card. If you don't have that, raise your hand. We'll make sure you get it. Everybody? So the things you need are the instruction memory, front and back, which are printed one-sided. So there should be a version of the instruction memory that has the mnemonic representation, like this. So you need both sides. Yes. And you'll need the register file card. You'll also need a writing implement. If you don't have one, let us know. We'll find something. And you'll need some sort of a marker to represent the program counter. Can be anything, something small. So let me step through this card. So I think this matches the instructions that are on your card. So just to make sure we understand the nature of all of these instructions, right? We have adds that operate on two source registers, produce a destination register. Add I operates on one source register, and an immediate value writes that back to a destination register. We have branch if less than. So branch if less than is going to compare x3 and x2 in this case. If the first, so these are sources, right? This is one thing I really dislike about not just RISC-V assembly, but most assembly languages. There's no, there's no distinction between the destination register and source registers in the syntax. So you just have to know branch if less than does not have a destination register. These two are both source registers. So you're comparing the two source registers. If the first is less than, branch if less than LT. If the first is less than the second, then you want to take the branch. Otherwise, you want to fall through to the next instruction. So take the branch means the program counter is updated to this LP label, which is this instruction. Okay, any questions about what the instructions mean? Okay. So no better way to learn than by doing. So you are going to be the CPU. You have the instruction memory, which has the instructions on it, and you have the register file, which the instructions will update. You have your pen or pencil to write the updated values in the register file. Okay, so I think all the values are written before you read them, so it shouldn't matter what the initial values of the registers are. So what you're going to do is just step by step execute the, be the CPU. So what a CPU is going to do, it's going to fetch the instruction at the current program counter, right? So initially, point your program counter at the first instruction on the card. Instruction 0. Fetch that instruction, which means you're grabbing it out of memory. Okay, so look at it. Decode it. I don't know why I haven't described decoding it. Oh, okay. So at this point, for decoding it, flip the card over and see the mnemonic representation of the instruction. So we're not doing the actual work of decoding the bits, but we'll just use the act of referencing the other side of the card that has the mnemonic representation on it for us to decode the instruction. Figure out which registers are the source registers, access those values from the register file. So look at the register file. You know, you don't have to physically do anything other than mentally look up the values. Mentally, again, execute the instruction. What's the result value? And write it back. Okay, so executing the instruction is the job of this component right here, which is referred to as the arithmetic logic unit. It's performing arithmetic computations. And then writing back the register file, you can update in pencil or pen is fine, the register file value. And then step to the next instruction. So normally, next instruction, increment the program counter by 1 instruction. If it's a branch and it's taken, update to the label, and repeat. Okay, so just do that exercise, step through instructions, keep going and going, see if you can figure out what the program is actually doing. And I guess once you understand what it's doing, you can stop. Right? So there are some other parts that we're going to use later. The only ones you need for this one are these 2 cards. So just to step through this in case anybody is having trouble getting started, right? You are the CPU, so you're going to do these steps. So the first one is next PC. For the first instruction, that's just setting the PC to 0. You're going to fetch the instruction. Here's the instruction. You're going to decode the instruction, which means interpret these bits, which we're going to do just by looking at the opposite side of the card, which has the decoded instruction, which in this case is this one here. This is an add. The next thing we need to do is access the source register values. These two are the source register values, x0, x0. x0 has a value of 0, so I'm adding 0 plus 0. Next thing I'm going to do is execute the instruction. I'm going to perform 0 plus 0. That's going to result in 0. I'm going to write that 0 back to the register file into the destination register x1. Right, so just write 0 into the register file x1. And then repeat. So go to the next instruction, instruction 1. So PC update, you update the PC from instruction 0 to instruction 1. You fetch this instruction, decode it, just reference the decoded representation on the other side of the card. And again, access the register values, execute the instruction, write back the result, repeat. Has anybody figured out yet what the program does? Don't say it, but I'm just curious. All right, good. So keep going through. So I think maybe half of you have gotten there, half of you maybe haven't. That's okay, no big deal. Um, so somebody want to say what the program is doing? Yeah, summing the first 10 numbers. So I'm not going to step through in detail, but I think you've all gotten far enough in the program to start to realize what it's doing. So okay, so the way the course is structured, it's structured in modules, right? So we're just wrapping up the first module, which is kind of introductory stuff for folks who are not familiar with this domain. So we covered digital logic, sequential logic, pipeline logic. We looked at tiny tape out. We used the FPGA demo boards. We used Walkwi and microchip. We built a calculator circuit and compiled that for the FPGA boards and worked with it. We ran into our debouncing issue, and next time we do the build, we'll see if we can fix that. And then today we looked at CPUs, compilation and assembly, program execution. So the way this is structured, Module 2 is meant, so students who have good experience with an ECE curriculum may skip Module 1. I know everybody that's signed up for this course, and I'm happy to see it, is signed up for all the modules. We're all doing it together. So just to realize that the progression of the slides is structured to sort of reintroduce the basic concepts, but go over them more quickly. So I'm going to go quickly over all of that since everybody was participating in Module 1. But we start off with a refresher. So we'll do a couple more little logic exercises in TL-Verilog. And probably skip the tiny tape out, but we'll see. I think those who are kind of racing ahead can, we'll do a couple updates to the calculator circuit. If you're ahead of the game, you can try to tape that out again, or rather implement it on your FPGAs. And then a quick review of the RISC-V ISA. And then, well, actually, no, it's not a quick review. A deeper dive into the RISC-V ISA. After that, we get into building the RISC-V core. So we're going to start with a subset CPU core, which is enough of the core to execute the test program that you guys just executed. After we build that core, the next thing we're going to do is pipeline it to stretch out the, all the steps of executing the instruction over multiple cycles. We're going to deal with, the difficulties that are involved when you overlap the execution of instructions. And then we're just going to go back and complete all the remaining instructions of the RISC-V instruction set architecture. After that, we get on to final projects. So team formation, I think for this group is easy. You're already sort of in tables. So your table is your team. If you're sitting by yourself at a table, you might want to jump in with a table that has just two or something, just so you have some teammates. My target was 4 to 5 students, but 3 students should be fine as well. It looks like all the most tables have 3. The 2 tables with 2, you can pick the people you like the most and offend the others and just jump in on one of those tables. So I've given you the cards already. So kind of the ground rules here as we're going through the exercises. The exercises you've done so far, kind of warm-up exercises, they'll get progressively more interesting. So the kind of airplane rules, put on your mask first, right? Do the exercise yourself first, and then look around to see who else needs help with their mask. As you're helping other folks, teach others to fish, right? The idea is not to give them the answers and get them done. The idea is to help them understand what the exercise is teaching them. So finish the exercise yourself and then help others with any confusion they have. You've all seen MakerChip. I don't need to demo that. You've done this one. You understand basic logic gates. So let's do another simple example, just again for a little more, a little more practice with TL-Verilog. So this one's very simple. Again, this is the starting exercise for folks who are jumping in and seeing this for the first time. But this example is an egg sorter. So we want to know whether an egg is large or medium. So this is the circuit that we want to build. So I asked ChatGPT what the size was for a large egg, and it said 65 grams or more. So you want to take in the input weight and see if it's greater than or equal to 65 grams. If so, assert this output signal large, otherwise don't. Okay, so open up a clean MakerChip session and go ahead and code that. I just pulled up this example as a reference for syntax. Srinivas, I'm sure. Yeah, hopefully that one was easy. So I'll just do that here. So we're assigning large as weight, which is 7 to 0, is greater than or equal to 8 tick D 5 6. Okay, simple as that, right? We're not worried about the test bench, just the logic. It's just a comparison. Don't worry about all that. All right. So next, is just to use a different encoding on the output. So instead of producing a 1-bit signal that's large or not, I want to encode this using values 1 and 2 as a 2-bit number. Okay, so same logic, just a different encoding of the information at the output. Right? If it's large, I want a value of 2-bit 2. If it's medium, I want a 2-bit value of 1. I'll step it through as well. So instead of large coming out, we want size coming out as a 2-bit number. Same comparison. If the weight is greater than this value, then we want an output value that's a 2-bit decimal 2. Otherwise, 2-bit decimal 1. And to leave no room for confusion, we can put parentheses here. The order of operations don't require it. Any question about that? Right? Anytime we're introducing a multiplexer into our design, we'll use a ternary operator or a chain ternary. Next, let's add another weight category. So let's support extra large eggs as well. So extra large eggs are greater than 64 grams according to ChatGPT. So add another multiplexer or another case, and we'll encode extra large as a value of 3. I'll do this one as well. Since we have more cases, I'm going to format it to be a bit more readable. Yeah. What? You have errors? Okay, so the thing to be careful of is to make sure you get the priorities right. We want to make sure that, well, so I put the weight greater than 64 first, so we could take care of the extra large case. It's not the extra large case, it's the mux that we had before. Any questions about it? And looking at the waveform, very few times did I actually get a large egg. It's a fairly small range, but there are a couple here. So that's a decimal 61, which is large. Seems to be behaving correctly. Everybody's got their cards from yesterday, right? The colored cards. Don't be afraid to use those. Just a quick review of pipelining, right? We can express pipelines very compactly by expressing that we're in a pipeline and we're in pipeline stages, such as that. Just about all of you have seen Verilog before, so I can relate this to Verilog for you as well. You can code Verilog any number of ways. This follows basically the recommended coding practice that I used when I was at Intel. So you see a nice code reduction by not requiring the signal declarations, not generating the flip-flops from context. So then we looked at changes, right? We can take a look at the Verilog level as well. The change in TL-Verilog is only to the staging. It's guaranteed to not affect the functionality, whereas in Verilog, the change kind of ripples everywhere, and it's very bug prone. Yeah, so this is the change in Verilog. So notably, we're following a naming convention here where the stage numbers are part of the signal names, right? So as we stretch out this pipeline, we need to add flip-flops to support the extra pipeline, pipe stages. We need to rename signals, so this assignment of CC changed from stage 3 to stage 4, so we're assigning it at a different stage, different pipe signal name, or different signal name to reflect the pipe stage. Adding flip-flops here, so pretty torturous representation of several months of my life. So I think we've explored pipelining enough. Let's do another exercise with pipelining. So to set context for this example, we have a pipeline. We're doing some computation in the pipeline. I don't care what the computation is that we're doing. The logic that we're looking at here is simply accumulating error conditions from that computation. So that computation has various types of errors: bad input, illegal op, overflow, divide by zero. They're triggered at different stages in the pipeline, wherever that related computation happens, right? And the logic that we're looking at here is simply accumulating those error conditions to produce at the end of the pipeline a signal that says there was an error. Okay, don't care what it was. So we're just taking these various conditions and ORing them together as soon as possible. We have another error here, we OR that in with the others. Another error here, we OR that with the others. So the blue circles are just ORs, OR gates. And the red circles are the signals that are, as far as we care, the inputs to our circuit. Okay, so just syntax reference here of Pythagoras' theorem. Double vertical bar as your logical OR. And see if you can code this up. It looks like a complicated circuit, but you'll find it's quite simple. Remember to show me your green card if you're all done. So basically, for this example, you'll know you're done if your diagram looks like what's up there. Okay, I think we're ready to move on. So again, I'll walk through this. So just in case anyone had issues, we have a comp pipeline that has logic in stage 1 that is producing error 1 as the OR of bad input and illegal op. We have logic in stage 3 that produces error 2 as the OR of error 1 and overflow. Technically, I had an underscore there. Come on. And logic in stage 6 for error 3. It's error 2 or div by 0. And the diagram matches. Everything is good. Any questions? Good. All right, so I think we may be time for a break. Let me just check and see if they're ready up there. Are we ready for break? Okay, so 15 more minutes. Fibonacci series we looked at before. We put it in a pipeline. I'm going to skip over that one. I'll let you guys vote here. Whether you want to see me code this up just as a demo of more pipeline logic, and yeah. Okay. So let's see. So this comes from one of the examples in MakerChip, one of the tutorials. So let's go to the tutorial for alignment. I think that's the one. Yes. So we're starting here with the Pythagoras' theorem computation that we looked at before. And what I'm adding on to that is an accumulation of distances. Okay, so if we take a number of hops where the hops are defined by a forward distance and a sideways distance, and we keep taking hops, I'm just accumulating the total distance of all of our hops. Okay. Yeah, I think I should use, I should start from a different one. So I'll start from this one. Do have valid, I'll keep that. Okay. So here's my starting point, and I'll go ahead and leave valid. No, we didn't talk about this yet, did we? No, so I'll get rid of this. So here's my starting point, Pythagoras' theorem computation over 3 cycles. And I'm going to add logic to accumulate the computations. Okay. So the logic that I want to implement is going to, each time I do a computation, add the result to the previous running total. So I've introduced a running total here. That running total is state. We need to reset that state. So I'm going to reset it to 0. And I also am introducing a valid signal. That was part of my original code here. I'm generating valid to be a probability of 1/4 just by ANDing together 2 random bits, right? So about 1/4 of the time my data will be valid. And we can look in the simulation. Actually, I haven't introduced that yet. Never mind. Let me recompile. So 1/4 of the time my computation will be valid. And when it's valid, I want to accumulate the result. When it's not valid, I just want to hold on to the result. So those are my 2 paths. If it's not valid, I want to hold on to the result, which, as we've talked about before, in TL-Verilog, you code that as a recirculation through a mux. If we're valid, then I want to select the accumulation of the total distance and the new computation. Any questions about the logic diagram before we look at the code? Well, both. I mean, it's saying we have a valid computation that we're performing that, is a valid hop. Otherwise, we're not hopping. Right? So, yeah, if the inputs are valid, we're doing a valid computation, we want to use that result. Okay, so to code this picture, right, when you're coding TL-Verilog, the first step is to get the mental picture in your head using these contexts, pipelines, pipe stages, figure out what the logic is that you want to implement. Once you have a diagram that looks something like this, it's just an exercise of translating that to code. So, this is the very manual step of just translating the diagram. So in stage 4 here, I have an expression for total distance. And my computation here is using bytes. That seems kind of small for an accumulated distance. So let me change this to 31-bit values. And just do everything as 31 or 32 bits. And the inputs, let's see, what am I doing? Let's make those 31. So my total distance, I'll just stay consistent. Everything will be 31, 0. So my total distance is coming from this mux. This mux has a reset condition. I'm just directly hooking up the system Verilog reset signal. It's a little bit cleaner to create a pipelined reset. That makes the code properly timing abstract, right? When I refer to a system Verilog signal like this, if I change this from @4 to @5 for some reason, I'm not guaranteed to preserve the overall function of the design because I'm not using pipe signals. Okay, so if I change this from 4 to 5, I'd be hooking up to the same reset signal with a different timing, and that can affect the function. But anyway, to be consistent with my diagram, I'll use reset. When we reset, we want a value of 0. That's a 32-bit 0, so I can use the shorthand. And I'll just be consistent here with my syntax. Those on separate lines. So reset to 0. Otherwise, if we're valid, I want to take the accumulation. So this will be my input from the adder. So the expression for the adder is CC plus the previous total distance. Right, so looking at the adder, I have this input, which is total distance from stage 5. Since my expression is in stage 4, and I want the total distance from stage 5, I have to reach ahead. So that's ahead by 1 total distance. And then my default case is to retain the value, which again is a recirculation from stage 5 to stage 4 of total distance. So that's this last case here. Any questions about that? I'm going to trust that it's behaving correctly. Total distance, we'll just make sure it's incrementing bit by bit. Okay, so we're getting completely random values on the input. Maybe it would be good to constrain them. So let's do yeah, we'll put that here. So you'll notice I separated my stimulus from my DUT. Okay. You know, more formally, I would have Verilog module definitions distinguish them, but I just separated them out in the code order. And yeah, so that's what I was going to say is you'll notice I have calc here and then I repeat calc again. It's perfectly fine. I could define some logic in this context of calc and stage 0. Then I could put myself in some other pipeline and define some other logic at stage 87 of that pipeline. Yeah, and then in my code I can return to the calc pipeline, add more stuff in that context. It's perfectly fine. It's something that, for lack of a better name, I've termed lexical reentrance, right? In the program order of your text, you can enter a context, exit that context, re-enter that context, define things. Seems kind of unimportant, but it's actually incredibly powerful aspect of enabling functionality to be put into libraries, right? You can get some of your functionality from libraries, some of your context from libraries, and then sprinkle your own custom logic within that context. And that's actually a very powerful feature of the language. So anyway, now that I've explained that, up in the stimulus part, just to constrain my inputs a little bit, I'll do this in stage 0 as well. Let's provide assignments for A and B, as we did before, to, I don't know, let's say 28 bits of 0 concatenated with 4 random bits. And then same for B. And of course they need to be different rands. So we'll make them 1 and 2. So this just constrains my inputs to be random 4 bits. And should be more meaningful in the simulation. Let's see, so my total distance, we can see marching up, seems reasonable. Valid is oddly regular here. Coincidental, I guess. Any questions about it? Yeah. Yeah. Let's see. So you'll notice in the logic diagram, it's all one pipeline, right? It's just the way I've organized my code. So that just allows me to separate off the aspects of the code that, to me, are the test bench from the aspects of the code that are my design, right? So, my test bench is driving a value of valid with a probability of 25% by using this random signal, and driving these with small numbers by using this randoms, right? So this is just to provide input to my design under test. Um, so, perfect, exactly the same thing if I did that, but code-wise, this just helps me organize my thoughts a little bit, right? But you can see in the diagram, it's all one. Uh, any other questions? The name lexical reentrance, by the way, turns out was a really bad choice, because at work I sit at my desk, I've got my Amazon dot next to me, and every time I say lexical, she asks what I want. Uh, all right. So how are we with the... Okay. So let's take a 15-minute break. All right, let's start up again. So when we last left our calculator, it looked like this. We're going to play around with the calculator a little bit more. I do have starting point code for the calculator as we left it. You can either pull up the calculator that you created, or if for some reason you lost it, you can pull up the one that I have. You can find that in the course repository, which I guess I don't have open. So there's a link here, calculator in module 4. That's not module 4 for us, but anyway, that's the link. So I guess I will open it, use that one. So we're going to play around with pipelining a little bit. I think one of the tables was actually kind of doing this on their own, but so right now our calculator, it executes in a single cycle, and every cycle we can do a new computation. Let's say our clock is running too fast to allow that, right? Maybe we only have time to do the arithmetic operations in one cycle, and we need to save the multiplexing for another cycle, just as an example. So obviously, if that's the case, we can't do back-to-back calculations every cycle. We can do back-to-back calculations every other cycle. But we might be constrained. We might have to separate it across 2 cycles and limit the throughput. So yeah, so I guess one thing to note here is that since our equals in is hooked up to this edge detector, it's already the case that we cannot produce a valid in back-to-back cycles, right? You can't have a falling edge in back-to-back cycles. You have to rise and fall. So the closest valid pulses can be is already 2 cycles apart. So we'll never be attempting to do back-to-back calculations, which works out well here since it takes us 2 cycles to update our calculator state. So the first lab is to work toward this implementation. We can do this in 2 steps. So the first is to introduce a new cycle in the pipeline, which we can simply do by, instead of looping back the output from the previous cycle, or 1 ahead in the pipeline, instead we loop it back from 2 ahead in the pipeline, back to val 1. Okay, so that's just a reassignment of val 1 to look ahead 1 more stage. That's the first change. Then verify that, and then actually this was too crowded on one slide, but we'll look ahead. After you make that change, we'll then slide the mux from stage 1 into stage 2. So that's just a reassignment of the stage, which again is a safe operation. Verify the behavior. Oh, I don't know why this is in 2 slides. Okay, so I guess we're just sticking with this one. This has the whole thing. So changing this to two stages ahead, retiming the mux. When you retime the mux, currently the visualization is in stage 1, so it's expecting to find signals at stage 1. The visualization won't work that way. Soon it will, but at the moment it doesn't. And so you have to move the visualization now to stage 2. So in the visualization, you'll be seeing your inputs that come in at stage 1. You'll be seeing the calculator update in stage 2. So if you're trying to correlate the input switches to what you see in the visualization of the calculator, they're going to be offset by a cycle after this change. But you'll change the calc-viz macro instantiation to give it a parameter of 2, which makes the visualization relative to stage 2 of the pipeline. Also, we currently have the inputs and the outputs all coming from, I think it's stage 1. Let's change the output hookup with the 7-segment display logic. Let's change all that 7-segment display logic, which is fed from out, now to stage 3. Okay. So I think it's all currently jammed into stage 1. Let's stretch this out, give it its own cycle now after our stage 2 logic. So we'll put it in stage 3. Okay, any questions about those steps? So again, changing this to a 2-cycle loop, moving the mux from stage 1 to stage 2, and retiming the things that are dependent on this circuit, which is the visualization and the output logic, which will move to stage 3. Clear enough? Again, if you don't have your calculator from before, this is the link. Calculator in Module 4. So I didn't realize this, at least in this code, I have the inputs coming in stage 0. So I guess currently in your code, if this is what you're supposed to have at this point, you will see that time difference between the input switches and the values in the calculator. we're ready to move on here. So I'll again walk through this myself. Any other questions before I do? All right, so hopefully if there are any remaining doubts, this will clear them up. So the steps are first to change the critical path, the loop from output back to input to be a 2-cycle loop instead of a 1-cycle loop. So this is the path here that's assigning val 1 as originally the previous value of out. And that's here. So this becomes a 2-cycle loop. And I can simulate that, check the waveform. Next is to retime the mux to stage 2. So we're moving the mux from this stage to this stage. My mux is here. So let's move that to stage 2. I also want to retime the visualization to stage 3. And by the way, I'll try to remember to I'll update the slide now. Well, I'll hopefully update the slide later. At this point, the design is broken until we do step 3, 4, and 5. So step 3 is to retime this logic to stage 2. Step 4 is to retime the visualization by changing this parameter. Make that stage 3. And, oh, sorry, I said 2. And then retime the 7-segment display logic, which would be this. 2, 3. Okay, so based on the assumptions of timing, we have to stretch this out over 2 cycles. So this must go to a 2-cycle loop and we must distribute the multiplexer in the next stage. And just to make that work, we need to stretch out the 7-segment display into stage 3, and we need to change the visualization just to keep the visualization working. The complexities involved in making this a 2-cycle loop are kind of just work naturally by the fact that the edge detector is not going to generate valid operations in back-to-back cycles. So we kind of lucked out there. And then it's probably worth noting that we still have this 1-cycle loop here holding on to out for invalid cycles. So any questions about what I did there? So in the visualization, you know, now that we've stretched it out, you're going to notice that these, which are a reflection of the Verilog input pins, and the 7-segment display, which are a reflection of the Verilog output pins, those are now separated by 3 cycles. I think it's 3 cycles. And the visualization of the calculator is in at 2. So I think the timing we have now is this at 0? Let me check. Yeah, so these are stage 0, this is stage 2, and this is stage 3 now. So you'll notice that time difference when you're trying to align these related things. Questions? Okay, so changing gears. Just stepping back, and this is a note about syntax, TL-Verilog syntax. So TL-Verilog has various types of identifiers. We're using pipe signals. Pipe signals start with a $sign and use lowercase names with underscore delimitation. Other identifier types, and we're not really going to use them, but just so you're aware, use different case. So generally this is something that's left to coding conventions in a language, right? Your organization might have a coding convention that classes use camel case and methods use lowercase and things like that. Global variables should start G underscore, what have you. Those kinds of conventions, again, lead to confusion when you're working with somebody else's code, right? So your organization can kind of establish a mandate that your code will follow this convention. And then you end up grabbing code from some other project or some other group or some open source project, and it's of course not following that convention. Much better to bake that into the language itself and be strict in the compiler to enforce uniform conventions. So what's generally a convention in most languages is part of the language specification in TL-Verilog. So camel case means something different. We're not going to use it, but it's called a state signal. Uppercase means something different. We're not going to use it. It is used in the template. You might see $any in some of your error messages in uppercase. Those are keyword signals. The naming, if you have numbers in the name, so the name is composed of a series of tokens, right? In this case, the tokens are pipe and signal. If you're using camel case, here the tokens are camel and case. If you're using numbers in your signal values, they should immediately follow the token. All right, so just having a number floating in space as its own token is not legal. The compiler right now is allowing is being a little flexible about these things, but to be strict about things, you should follow this convention for your pipe signals. Don't cares. Who's familiar with don't cares? Just to get a sense. Okay, pretty much everybody. So a don't care represents a value that could be a 1 or a 0. It shouldn't matter. Our simulator in MakerChip is an open source simulator called Verilator. Verilator is a two-state simulator, 1s and 0s only. It does not model don't care state. So we don't have the benefit of don't cares in MakerChip. There's a 4th state, Z, for undriven. So the world has sort of shifted away from that design paradigm of multi-driven buses, which would have Z states. They're hard to analyze. So they're rare, but not unheard of. Okay. So TL-Verilog introduces a concept that's similar to don't cares, but a little more high level. So this concept of validity. So we looked at the Pythagoras' theorem computation before, right? That's what we have here. And here I'm adding to that this notion of validity. So valid is a signal, just like any other signal. There's nothing special about it until I use it with this notation, which you can read when valid. Okay, so I have valid, whatever it may be, right? Our calculator has a valid signal. This notation, when valid, is applying that valid signal as a when condition to the entire pipeline. And it's saying, only when valid is asserted am I doing a meaningful computation. It's actually, if you look at most circuits, most of the time they're not doing anything meaningful. They're just waiting for something to do. And it's nice to have that knowledge baked into the model of when the hardware is doing something meaningful and when it's not. You can use don't cares to convey that. You can sort of manually inject don't cares into the simulation. This helps to catch error scenarios that don't care will propagate. If you inadvertently consume something that you think you shouldn't care about, you can catch it. Validity is similar, but it's applied, in this case, to the entire pipeline. So a number of benefits from incorporating this awareness into the model. The first is debugging becomes easier. So instead of looking at a waveform that's just a sea of values that's hard to sift through, the waveforms that you're looking at can look more like this, where it's very easy to see kind of the valid data flowing through in a pipeline. It's easy to see what's valid and what's not. Everything that's been turned red, you know you don't have to worry about. So your designs are cleaner with more awareness, more information, less noise. You get error checking as a result of this, right? Again, if you're reading something that you're saying is garbage and using it in a computation that shouldn't be garbage, you can catch errors that way. Today we get that from injecting X's in simulation from this knowledge of validity. In the future, we could imply assertions that would be generated automatically from this and more directly catch issues. We also get something called clock gating for free. Who's familiar with clock gating? Okay. So clock gating is a power savings feature. If we know that the data that we're computing is invalid, right? It should be garbage. There's no reason to propagate garbage through a flip-flop. A lot of the power in a digital circuit comes from the clock, right? The clock is a signal that's oscillating twice every cycle. So there are a lot of transitions and those burn power. That transition is getting distributed across the entire chip. That burns a lot of power, and that connects up to pretty much every flop in your circuit, and the flop is consuming power on that transition. So there's a lot of power burned by the clock network and the transitions of the clock. If we don't need to transition data from one side of the flop to the other, there's no need for a clock edge. So what we do with clock gating is we cut off the clock pulses that we don't need. So if we know we don't need the pulse, cut it off, and thereby save the power that's consumed by distributing the transition. So with the knowledge of validity, we have knowledge that enables us to apply the clock gating and avoid the power consumption. Yes. Say that last question again. Right. So we know whether it's garbage based on the when condition. Right. So this valid signal becomes the clock gate condition. Okay. So if valid is deasserted, we know this computation is garbage. The designer's telling the circuit it's garbage if it's not valid. And therefore, we can generate a circuit that disables the clock edges for the invalid cycles. Okay, so in this case, with the pipelined logic and the knowledge of validity, we're going to get pulses that look like this. So these pulses correspond to a valid calculation when the valid signal is asserted. This is 3 stages of a pipeline, so this flop is a cycle after these flops, so we would see a valid pulse, a clock pulse for these flops, and then a cycle later, that valid pulse for this flop. So these would be 2 separate clock gators, one for the first rank of flops, anything going from stage, whatever it was, 1 to 2, and one for everything going from stage 2 to 3. I mean, the circuit is really doing something. Right. So, I mean, the actual hardware is going to have a 1 or a 0. It's predictable which one it has, but in simulation, you'll simulate with an X so that you get these benefits, right? I didn't follow. Trace what backwards? Sorry, calc 0. The, oh, here. Right, the actual hardware will have something, but you want to prove in simulation that you're not dependent on that something, right? Your machinery works regardless of what that value is. And if you can, if you can prove that the value doesn't matter, you clean up your world. You go from this sea of values to this limited set of values that you need to focus on to verify the functionality. Correct. Anything that's state, like the accumulator, it's holding on to value that carries from one transaction to the next. Right? It's valid for all of time. Those signals will always be valid. They don't always have to have a clock, though, right? They only have to have a clock to transition. So if you have, for example, the example that I demoed before with the accumulator, right? The accumulator can be conditioned on the same valid because those are the conditions under which the update happens. Other cases, you're holding on to the value. We did that with the recirculation. We also don't need the clock. Okay, any questions about validity? Yeah, well, I'm not sure if this is what you're saying or not, but right. Yes, so that's reset methodology, right? That's the methodology by which you verify that reset works. You assign every state in the design to don't care. Reset should put you into a known state, right? When you power up your circuit, you literally don't have any guarantee as to what the values in the circuit are. You simulate for a while, and that should clear all the don't care state to a known state. So you're verifying that the application of reset is getting you into a known state. And that's what Professor Boku is alluding to. Yeah, I mean that's one use of this knowledge is to generate your clock gating logic. And that the valid is the enable for the clock. How do I verify that the enable is not generating a spurious edge on the clock? Yeah.
But beyond the positive edge. So will the gated clock will generate a spurious edge which might match the data?
You're worried about a kind of a race condition on. So we have a clock signal.
The off period.
Right, right. Yeah, so I think what you're saying is you've got a valid signal that goes along with this. This needs to shut off the clock edge, right? And if you really designed your circuit like this valid signal would be transitioning for some period and stabilizing on a stable value.
What I'm saying is that can you make the valid signal a little some offset? Like during the on period of the clock, the valid signal is going high. Like this.
Right.
So now if I gate the clock and the enable, I'll get one small edge. Is it it's AND gating, right? Clock gating is
That's right.
kind of, so
Yeah,
that is-
so you need to be careful of this, right? The clock gating logic needs to be designed so that you guarantee that the valid pulse is successfully squashing the clock pulse, right? And that's part of the clock gating methodology and the way the clock gating logic is generated. You wouldn't do it this way. You need to be able to generate the enable early so that you're successfully, yeah, so that you're successfully squashing the entire clock pulse. TL-Verilog is logic level, right? And so it's the sandpiper in this case is responsible for generating code that the downstream tools will ensure, you know, don't have this race or timing issue. Sorry, valid logic needs to what? So valid could be anything, right? It's just a signal in your design. You need to assign it appropriately.
right, but the timing and all that.
Yeah, I think we'll see it. Either I will demo it or you'll see it when you do the next lab. So I think you'll see it. So I'll let you do the next lab, and as you do that, you can explore the waveform. Um, no, it exists in your hardware. It's part of your hardware model. Yeah. But TL-Verilog handles it. Yeah, yeah. So I'll let you do this lab, and then, you know, after I do it, we can look at the generated Verilog and the waveforms. So this lab is simply to use validity and apply that to your calculator, right? We already have this valid signal, which tells us when we're doing a meaningful computation. So this lab is to use that as a when condition, right? If we're not performing a meaningful computation, there's no reason to, you know, these arithmetic operations are invalid. Therefore, for clock gating, for example, there's no reason to provide the clocks for the flip-flops that are carrying the result of this computation through to the mux. And there's no reason for us to look at the values in the waveform. We should know that we're not using them. So this lab is simply to take the existing valid signal and apply that as a when condition to the arithmetic computation here. And verify that in the waveform. So, sorry. All right, I thought I had a little reference here for the syntax, so let me do this side by side. So if we have, I'll just put it in my calc pipeline. So if you have a valid signal, which actually we do, to apply that valid signal as a when condition, when valid, and then put your logic under this. You can actually do this one of two ways, right? You can have your valid condition like this under the pipeline stage. Alternatively, if you want to apply that to multiple stages, you can also do it this way. So those do the same exact thing. You know, in this case, I'm putting valid outside of any stage. So this isn't declaring the valid signal, it's using the valid signal as a condition, as a when condition. So the assignment of valid, yeah, it's down here. So this is actually broken because I'm trying to use it in stage 0 when it's assigned in stage 1. So let's change that to a 1 and bring this back to 0, for example. But syntactically, it's just adding this condition, and you can do that either outside of or inside of the pipe stage. Whatever is under, whatever's indented under valid. So in this case, it's just this expression is affected by the valid, or we're only applying this when condition to this one statement, right? And again, I could instead do this the other way around, right? If I structure it this way, I'm only applying that condition to logic in stage 1. So it's just a question of whether you're trying to apply the when condition across an entire pipeline or just to localized logic. Either way is fine, and you can repeat the valid, right? So if I had other logic in stage 2 that was under the same valid, I can repeat it. This would be the same, just to kind of complete this, bar equals something. Right, so this expression of code would be identical to that. Right, so whether the valid's on the outside or on the inside, same thing. It's just kind of an attribute associated with whatever code is under it. Yeah. Yeah, anything that's indented under the valid. And it's not, just because you have an expression that's under the when condition doesn't imply any gating. The gating only happens when you flop the thing that's got the condition on it. Right, so any flops of the conditioned signals get gated. So if I actually consume foo in stage 2, that means there's a flop on foo from stage 1 to 2. That flop will be gated. And there are command line switches to control the heuristics for clock gating, or the methodology for clock gating. If you're on an FPGA, you don't use clock gating, you use clock enables. So there are switches that say, generate clock enables, or generate clock gating, or don't generate any. Okay, but the exercise here is simply to apply the when condition to these computations. Mhm. That works. Yeah, that's what. It's doing well with this. It's pretty straightforward, actually. 0. Ah. Okay. So if you need to catch the bus, yeah, we can do it after lunch. Okay. See you after lunch at 2:30.